Hello, and welcome to this discussion of electromagnetic waves. In this discussion, I am going to talk about electromagnetic waves in a phenomenological way by talking about how they can be produced and detected. And later, we will go on to discuss them in the context of Maxwell's equations and show how those equations require some of the things we're talking about today. So let's start by imagining you have an alternating current in a wire. So when this happens, at sometimes the current will be in a direction such that the electric field is pointing upward, as it's showing here in this top left picture, and that will cause electrons in the wire to be forced to one end and positive charges to the other. Then at a later time, when the current is zero, then there will be no electric field in the wire, so the charges will be equally distributed. Then at a later time, so halfway through the oscillation, the current will be in the opposite direction from where it began, which means you'll have negative charges at the other end and the electric field pointing at the opposite direction. So, but by just having this oscillating current, we're creating a changing electric field in the wire. Now, when we change the electric field or any field in one location in space, it doesn't just instantaneously change that field everywhere. It takes time for those changes in the electric field to propagate through space. And in fact, those changes propagate at the speed of light from wherever the charges actually are. So when you have something that's continuously oscillating, then those changes in the field propagate through space in a sinusoidal oscillation. We talked about how if you have this oscillating current, you get an oscillating electric field. And so what you also know is that if you have current in a wire, that produces a magnetic field. So you can figure out the direction of the magnetic field by using the right-hand rule. If you point your thumb in the direction of the current in the wire at a given moment, then your fingers will naturally curl in the direction that the magnetic field takes around the wire. So if the current at some instant is upward, like it's showing in this lower left-hand picture, then the magnetic field on the side of the wire where we're examining the electromagnetic wave will be pointing into the screen. And then later it could be pointing out. And so we would also get an oscillation in the magnetic field that propagates through space at a finite speed, at the speed of light. So just because of the way magnetic and electric fields are produced, we can see that these fields have to be perpendicular to each other. So when the electric field is going to oscillate up and down because the charges are moving from one end to the wire and the other. But then the magnetic field is going to circulate around the wire and be perpendicular to the electric fields. Also, when the current is maximum, that's where you're going to get a maximum electric field. That's also when you're going to get maximum magnetic field. So the electric field oscillation and the magnetic field oscillation will be in phase with each other. One thing to point out is that we're just looking at part of the electromagnetic wave that propagates to the right from this wire. But there's going to be electric and magnetic fields propagating in all directions in three-dimensional space. It's just easier if we focus on the wave as just in one direction and sort of examine it that way. But it is important to remember that when you have a source of electromagnetic radiation, it's isotropic. It spreads out in all directions equally. So we can transmit electromagnetic waves, but then these electromagnetic waves are just oscillations in electric and magnetic fields in space, and fields aren't really real. They're just a way of visualizing the forces that particles exert on each other. So a moving particle can exert magnetic forces on another charged particle, and a charged particle can also exert electric forces, and that's described by the Lorentz force here. So if we want to actually detect electromagnetic waves, we need them to interact with some other charge. So we have our transmitting antenna here with its oscillating, a single oscillating charge moving up and down, and you can see how that produces these changing electric fields. So we're just looking at the electric field here, and this animation is showing how those changes in the electric field take time to spread through space until they pass by this receiving antenna. And so when those electric fields pass through the antenna, the charges in that antenna are moved up and down by those fields, and that transfers energy to those charges. And so that, then you can have that produces a current in the receiving wire here, and that can be used to drive like electronics, an amplifier, a speaker, and send sounds or data. So electromagnetic waves can carry energy and signals. So some other properties of electromagnetic waves are that we can describe them using these equations. So as we already explained, the electric field and magnetic field are always perpendicular to each other. So here in this animation, we're showing an electromagnetic wave propagating in the x direction. And so then the electric field is only in the y direct, only has y components, even though it only varies in the x direction. So that's why it's only a function of x. And it is a sinusoidal function. So it's a function of both space and time. And it's got a wave number, which is related to frequency, and an angular frequency, which is related to the frequency and the period of the wave. There's also a relationship between the magnitude of the electric and magnetic fields, and that's given by this expression here. They're related by the speed of light. So we've talked about how the electric and magnetic field have to be perpendicular to each other in an electromagnetic wave, because electromagnetic waves are produced by accelerating or oscillating charges. So just by the nature of the kind of electric and magnetic fields that an accelerating charge produces, the electric and magnetic fields will be perpendicular to each other, and they will take time to propagate through space. But the orientation of the electric field doesn't have to be vertical. As long as the electric and magnetic field are perpendicular, they can be rotated around the axis of propagation, the direction of propagation of the wave. So the direction in which the electric field is oriented, we call the polarization direction of the electromagnetic wave. We can actually see that light waves and electromagnetic waves have this property of polarization if we use a polarizing filter, as shown in this diagram here. If you take most light sources produce, like the light bulbs in a room, have many excited particles that produce electromagnetic waves, and these many different particles have excitations with a lot of different polarizations. So you get unpolarized light. That is light that is a mixture of electromagnetic waves with many different polarizations. So if you take a polarizing filter, like the filters in polarized sunglasses, then you can filter out the polarizations that are perpendicular to the polarizing axis of the filter. So light that is in the same direction as the polarization axis will pass through. Light that's perpendicular to the polarization axis will be blocked. And light that is at some angle to the polarization axis, the components of the electromagnetic, the electric field that are perpendicular to the polarizing filter axis will be blocked. So part of that electric field for waves that have polarization that is partially off axis will be blocked, right? So what you get is light that is linearly polarized in the direction of the polarizing filter's axis. So what a polarizer is in reality is usually some kind of material that has very long molecular chains, so usually some sort of plastic material with long molecule chains that are all oriented in the same direction. And when an electromagnetic wave passes through such a filter, if the polarization of the electric field is parallel to those long molecular chains, then it will cause electrons in those long chains to move back and forth. And it basically gives up its energy to move those electrons back and forth and is thus absorbed in the material of the polarizer. So the axis that allows light to pass through, the polarization axis of a polarizer, is actually perpendicular to the direction of these molecular chains. So as you see in this drawing here, the polarization axis is vertical, and the molecular chains in the polarizing filter are actually horizontal. So as discussed earlier, electromagnetic waves propagate at the speed of light. So this is approximately 300,000 kilometers per second in vacuum. In other materials, things that are not vacuum, the electromagnetic waves can interact with material and thus get slowed down. So the speed of light in materials is slowed down by a factor which is called the refraction index. And the refraction index is different for each material. The speed of light in vacuum is also related to some of the constants that are in Maxwell's equations, the vacuum permittivity and permeability constants. They're related by this equation here. So if you recall from some of our discussions of capacitors and inductors, in a capacitor, if you have, the basic idea of a capacitor is that it's two parallel plates that are connected in a circuit, and then charge can be built up, opposite charges on each side of the capacitor, which creates an electric field between the plates of the capacitor. But if you insert a dielectric material, right, so normally there's air, which is pretty close to being vacuum, between the plates of a capacitor. But if you insert material, then that material can become polarized, and that in effect changes the permeability, the permeability of that material by a factor of kappa, and gives you a different permeability constant for the capacitor, depending on what the material is inside the capacitor. So that's similar to the way in which the speed of electromagnetic radiation changes based on the material. And it just shows that all these constants are connected. So energy can also be stored in electric and magnetic fields, and we saw this when we studied capacitors and inductors, and specifically in the LC circuit, which is just a combination of an inductor and a capacitor. We saw that energy can oscillate back and forth between the capacitor and inductor. So energy is at sometimes stored in the electric field in the capacitor, and at other times stored in the magnetic field in the inductor. So the energy density in an electromagnetic wave comes from the energy stored in those electric and magnetic fields. That can be expressed either this way, where you're taking into account both the electric and magnetic field, but because of the equivalence between the electric and magnetic fields that we discussed earlier, that electric field is equal to the speed of light times the magnetic field, we can also express this in ways that use just the electric field or just the magnetic field as well. Sorry for the bad writing there. I'm trying to annotate with the mouse here, so I'm doing the best I can. So if we have this energy density, we can calculate what the total energy is in a cylindrical volume, and by calculating what that volume is that passes through, if we think of this as the energy in our electromagnetic wave, we can calculate how much energy is passing through a cylindrical volume from that wave in a given amount of time. And this gives us the energy flux, the energy per unit area per unit time that is passing through a plane that's perpendicular to the direction of the electromagnetic wave. And that's given by this vector S, which is just equal to 1 over the permeability constant times the electric field crossed into the magnetic field. And if we think about the direction of the electric and magnetic fields in a wave and use our right-hand rule, we can see that the cross product of these will always point in the propagation direction of the electromagnetic wave. We can also use some of the expressions that we had earlier for the electric and magnetic field and substitute and this equivalence here, and substitute those sinusoidal expressions in for electric and magnetic field and get a space and time dependent expression for this S vector, the pointing vector. So this gives us the time and space dependence of the energy flux in our electromagnetic wave. So that's interesting, I guess, but when we measure waves, we can't usually measure just the energy flux. We usually measure things like brightness, or if you're thinking of a sound wave, you might measure loudness or something like that. So what we're actually measuring is intensity, which is the time average of energy flux, usually the average over like a full cycle. So if you average a cosine squared or sine squared function over time, cosine squared has values that go from 0 to 1. No matter what the argument is, it's only going to give you a range from 0 to 1. So if you average over a full period of a cosine squared function, then you just get 1/2. So that gives us our formula for intensity, which is just 1/2 times the speed of light times the proper constant times the electric field magnitude squared. And we can again express these using either just electric field, just magnetic field, or a combination of the two because of the equivalency noted earlier. Now, if you have a point source of waves or electromagnetic radiation, then as it spreads out into larger and larger circular volumes, circular shells, then the intensity, the energy per unit area will decrease with distance squared from the source, just according to this equation here. So based on this, we could actually see that the electric field amplitude is actually proportional to is inversely proportional to distance, and we could express our electric field with space and we can express our electric field amplitude as having a dependence on distance. And then we can kind of see in this drawing here, I've drawn that as the as we move away from the source of radiation, the amplitude of the electric field actually decreases while it's oscillating. So in our other representations of the electromagnetic waves, we weren't showing this, even though this is what happens as you move away from a source of electromagnetic radiation. The amplitude decreases as 1 over r. So electromagnetic waves, normally light is an electromagnetic wave, but visible light, that is. But electromagnetic waves can have basically any frequency. And if an electromagnetic wave passes from one material to another, the thing that changes is the wavelength. The frequency always stays the same because that's time dependent. So if you have a peak in a wave passing into the medium at one point, then just on the other side of the boundary, there also has to be a peak, or there would be a discontinuity in the wave. So if you have peaks passing a boundary between two media at a certain frequency, the frequency has to be the same on both sides, but the wavelength is what gets changed because that changes in space, not time. So this chart here is just showing, giving an idea of the relative size of the wavelengths of different frequencies of electromagnetic radiation in air or vacuum. Of course, wavelengths will be different if they're in other materials. And then up here, it's also showing that some frequencies of electromagnetic radiation interact with matter in different ways. So, for example, our atmosphere absorbs certain frequencies or wavelengths of radiation very strongly, but things like visible light are basically our atmosphere is transparent to visible light, so it doesn't interact with visible light. So that's possibly why we evolved with the particular visual organs that we have that are able to see in this wavelength range. Also, radio waves pass through our atmosphere pretty easily, and that's nice because we can easily send radio signals that way and communicate across long distances. So, electromagnetic waves can propagate at a wide range of frequencies. Also, electromagnetic waves can be superposed. They can have a principle of superposition. So that means that we can form complex waveforms by superposing sinusoidal waves of many different frequencies. So that allows us to send complex information using electromagnetic waves. So a simple way of doing this is amplitude modulation, or AM. So all you're doing there is you're taking a carrier signal, some kind of high frequency signal, that so if you have a higher frequency signal, then if you want to receive a signal, you want your receiving antenna to have a length which has a resonant mode that corresponds to the wavelength of the radiation. So just like waves on a string, the wavelength of an antenna, the fundamental wavelength mode for an antenna is twice the length of the antenna. So when we make an antenna, we say that it's a half wave antenna. That means that it is half the length of the wavelength that is designed to receive. So usually you have a carrier signal that is short wavelength, high frequency, because then you don't have to make an antenna that is enormous. You can make a smaller antenna. Then the type of signals that we want to send are often things like audio, music, or talking. And those are generally lower frequencies, like in the range of human hearing, 20 to 20,000 hertz. So in order to send a signal with amplitude modulation, all you have to do is add them together. So then you get something that looks like this third waveform down here. You get something that is a high frequency wave that has an amplitude that varies slowly in the same shape as your modulating signal, your audio or music. Another scheme for sending information using waves is frequency modulation. This is where you vary the frequency proportionally to the shape of your modulating signal. And this is a bit more complicated to do mathematically. You can't just add the waves together. But it has advantages in that, so one advantage is that the signal has the same amplitude no matter what. So if your equipment is trying to amplify the signal, then your amplifier doesn't get overloaded by trying to, if you want it to be powerful enough to amplify the quiet parts of the signal for AM modulation, right, then it can get overloaded for the loud parts of the signal, right? So for FM modulation, the amplitude of the signal doesn't matter. It's the frequency, so your amplifier doesn't get overloaded. All right, so that's the end of our discussion on electromagnetic waves, and next time we will discuss Maxwell's equations.